All right, today we're going to take a look at section 12.5, which is talking about ratios of areas to each other. So we're going to take a look at figures and compare their areas to each other. There's three different types of problems in this section. This section is definitely one of the tougher sections in our book. And so what I'll do is I'll introduce three different types of problems on the front side, and then we'll try some examples of those types of problems on the back side. The first type of problem is probably the simplest type of problem, and that is basically finding both the areas and just making a fraction. So problem number one is an example of this. So for number one, I can find first the ratio of BC to CD. Let's find these lengths first of all. I know that this is going to be 5 here. This is a 5, 12, 13 triangle. I also know that this whole thing will be 9, 9, 12, 15 triangle, 3, 4, 5. So that makes this 4. So the ratio of BC to CD would just be 9 over 5. Next, if I want to find the ratio of the entire triangle ABC to the triangle over to the right, ABD, I'm going to simply find the areas of both of those. So to find the area of the entire triangle, it'll be 9 times 12 divided by 2, which is just 54. And then if I want to find the area of this triangle over to the right, I can do base, which is 4, times the height, which is 12. They have the same height, and divided by 2, which is 24. And this whole thing simplifies to 9 over 4. And that's the first type of problem. The second type of problem is finding the areas in terms of the common dimensions which divide out. So you're going to end up having some problems where a common dimension will divide itself out. And actually, if you take a look at this problem right here, you can sort of see what I mean by this. Let's say we didn't know that this was 12. We just know that it's some height. Well, if I wanted to do the exact same problem here, I could find the area of the entire triangle. It would just be 1/2. The base is 9, and let's call that height H. And I wanted to find the area of the triangle over to the right again. It'd be 1/2, the base is 4, and we have the same height, so guess what? The heights will cancel out, and the 1/2s cancel out, and you're left with the same answer, 9 over 4. So that would be an example of when the common dimensions divide out. This problem down at the bottom, I believe, is the same type of problem. Yep. And we're looking at AD bisects angle BAC. If you remember, we talked about earlier in the semester, we talked about how whenever you see an angle bisector, you should be thinking about the angle bisector theorem, which means that this ratio, 9 to 12, is going to be the same ratio. 9 to 12 is 3 to 4. The ratio of these parts down here is going to be in that exact same ratio. So let's call it 3x and 4x down here, because it has to be in the same ratio of 9 to 12. And if I'm looking for the ratio of the entire triangle to the triangle over to the left, well, I'm taking a look at this thing, and the triangle for the area of the entire triangle, let's go ahead and kind of insert a height here. Okay, this is going to be the height. So for the entire triangle, it'll be 1/2 of 7x, the entire base, times that same height that I drew in. And it's going to be divided by 1/2 of, so we're looking at the triangle over to the left now. 3x is the base of that triangle, and the height's the same. And again, the heights are going to drop out, the 1/2s are going to drop out, the x's are going to drop out. Your ratio of those two areas is going to be just 7 over 3. So those are examples of the second type of problem here. The third type of problem is using a theorem about similar figures. And so to talk about that, let's take a look at this problem up on top here. And so it says here that angle A is congruent to angle B. It says that x is to 3x here. And it also says that these are both right angles. So I know that by AA similarity, that these are similar triangles. And so I can take a look at this, and I know that if these sides are in the ratio 1 to 3, that the bottoms or the bases are also going to be in the ratio 1 to 3. So let's call this y and 3y. And let's take a look at the ratios. Just like we did for the second type of problem, the area of the first triangle would just be 1/2 of the base, which is y, times x, which is the height. And we'll divide that by 1/2 for this triangle over to the right here, 3y and 3x. And this is going to simplify. The 1/2s are going to drop out, the y's are going to drop out, the x's are going to drop out. It's going to be 1 over 9. And what you're going to find out here is that if the ratio of the sides is n to m, in this case it was 1 to 3, that was the ratio of the sides, then the ratio of the areas of the similar triangles is just going to be, you take the n and you square it, and you take the m and you square it. You take the sides and square it. So that's how we ended up with 1 over 9. We took the 1 and we squared it, and we took the 3 and we squared it, and we got 1 over 9. And so that's the theorem here. If you have similar figures, you take the ratio of the sides and square them, and that'll give you the ratio of the areas for similar triangles. Actually, that is the third type of problem that we're talking about here. And that does work for all similar figures. Okay, let's go now to the backside, and I'm going to go ahead and go over some example problems. Okay, moving on to the backside here, we're going to try some example problems. The first type of problem that from the front side we're not going to do too much of, but we'll do a lot of the second type and the third type. The first type, of course, is the easy type, where you're just finding areas and just plugging them into as a ratio. So here we're finding the ratio of the entire parallelogram to the area of this triangle over here. And so I know that this height is going to be the same for both types of figures. And this one, it'll be, the area is going to be base times the height. And for this guy, it'll be 1/2. And the base for this triangle is going to be the same as the base for the parallelogram. And the height's going to be the same. And so what we're looking at here is we're looking at 1 over 1/2, or 2 over 1 would be the ratio. Okay, if we take a look at the second problem here, I have these sides are parallel to each other. Hopefully you can recognize that the two triangles here are going to be similar triangles, because we have these vertical angles congruent. We also have alternate interior angles congruent to each other. So by AA, you know that those two triangles are similar. And so we're going to apply the similar triangle theorem. And basically, I know that this side corresponds with this side right here, the 8 and the 5. So if I square it, I know that the ratio of the areas will just be 64 to 25. It doesn't mean that the actual area itself is 64 and 25, but it means that the ratio of the two areas to each other will be 64 to 25. However, we're looking for the ratio of the entire bow tie to the triangle to the left. And so the entire bow tie together would just be, if I add these two up, 89. And if I look at the one on the left, it's 64 still. And so that would be the ratio of those two. And that's using the theorem from the front side that we're talking about with the similar figures. Okay, problem number 5 here. This is a trisected, so let's call these x, 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 bisected, y, and y. And probability that it's not in the interior of EDG. So we're just really looking at the ratio of this to the entire figure. Okay, so we're looking at the ratio of this part to it. And so what I'll do is I know that the entire figure is going to have the area of 3x times 2y. That's just the area of a rectangle. And I want to subtract this area right here, the triangle, which is 1/2 of 2x times y. And then I want to just divide it by the area of the entire figure. So it's 3x times 2y again. And go ahead and simplify this. I know that the top thing will simplify to 5xy, and the bottom would be 6xy. So this all just simplifies to 5/6. And we'll do one more problem here. This is a very common type of problem. This is supposed to be the parallelogram symbol. So parallelogram ABCD, if point chosen at random, what's the probability that it's not in the interior of triangle EDC? And so what I kind of need to do is just identify how these areas are compared to each other. And if I look at this thing, I know it's a parallelogram, so I know that these sides are parallel, which means that in a parallelogram, these two are congruent to each other because we know that the diagonals bisect each other. And so I know that these are similar figures, and it's in a 1-to-1 ratio. The sides are in a 1-to-1 ratio, so I know that these areas are going to be in a ratio 1-to-1 right there. So the top triangle and the bottom triangle are in those ratios, 1-to-1. And if I focus on, say, this triangle right here, and I just if I use this part as the base, so if I use this as the base, I know that the height will look something like this for both the triangle on the top, as well as triangle ADE, and I know that that's the height for also the triangle over here on the bottom for triangle DEC. And because these two bases for this triangle, as well as for this triangle right here, their bases are in a 1-to-1 ratio and the heights are the same. So I know that these two areas are in a 1-to-1 ratio also. And likewise, I can do the same with this one. They're all in a 1-to-1 ratio. So they're all the areas are the same for each of these triangles within this parallelogram. And so if I look at this thing, the probability that it's not in the interior is just going to be EDC is this triangle right here. Probability would just be that it's in these three triangles over here, so it's just going to be 3 over the total area, which is 4, or 3 over 4. Okay, hopefully that makes sense. We will now, I'll let you go ahead and try some of the problems on the homework. Keep in mind that there's, those 3 different types of problems listed on the front side, so look out for those 3, and let's see how you do. All right, take care.